什么108次 review，我不太懂为什么会这么多，然后其他大概就是10几个。为什么第一个就哇108个，这是为什么呢？我还蛮想知道为什么的。OK，好，那我们就开始上课了。嗯，OK，好，太多东西了。So last time we talked about the some when we finish PDF 2, and then we are move on to PDF 3. Uh, we in the beginning we talked about some useful mathematic technology, just like PDF 2, right? And you will notice that all the techniques tools will help us to find some knowledge deep inside that uh, you need to use those mathematic tools to find the underlying physical meaning, right? And also some relationship we didn't know. Okay, so that's we think those mathematicians who invent those such useful tools like Legendre transformation. Okay, change the variables, so you will see how it works later. Okay, or we found how to get rid of undesirable constants and also change variables by using calculus. And also last time we talked about how to find the implicit dependencies. Well, dependence means a relationship. Okay, so last time we stopped here, so let's continue. So we want to get the if we have the UTP, okay, we want to see the change of the internal energy due to the temperature change, okay, and also how at the constant P. All right, and we want to find this. And also we want to okay, we're going to find the relationship between them. Okay, so you see U and T and P. So U should be is typically naturally we will use regarded internal energy is a function of temperature and volume. Okay, and V can be treated as VTP like the PB Kotemati, right? So you can see how the relationship between them. So now we found that U is a function of TV, V is a function of TP. So we can find the relationship underneath. How to do that? Because you can see here is something not doesn't appears here. All right, so we want to get rid of this. So wanna sorry, too small. Wanna get rid of the V here. Okay, we don't want that V appear in this relationship. Although we know that U and T and P all connected to the V. I want to get rid of that. Okay, so you see, if we have this function, we can write down the U, change of U is has two contributions from dt and dv, and change of V has the function of T and P, right? So the change of the V has two contributions, dt and dp. All right, so this things is something that we are going to get rid of it. So all we need to do is just to substitute this dV, replace the dV by this ugly term. Okay, just substitute here, and we can write down such long things. All right. So the dt here, and dt here. All right. And constant p, so we can get rid of p. And then you find that if we switch the left-hand side, right-hand side dt to the left-hand side, we differentiate by t at constant p. So you can obtain partial u partial tp equal to this, right? So you can decipher, kind of decompose this partial u partial t with, I mean, if you don't know how to measure this partial u partial t at constant p, you can transform it into partial u partial t at constant v, and constant t and constant p, right? So it's kind of, you find that actually this slope can be decomposed into other thing. OK， 好，我们就来讲的是附带的含蓄的就是依附的关系，那是你看不出来的啊，我们使用数学方式来看得出来的。例如说我们想要知道这个，那我们想要知道这个的话，可是我们想要知道它就如果这个东西很难算，那我们想要用别的方式去算出来。好，那我们就可以去拆解它。那这个拆解它要怎么办呢？我们就看 ，OK，U 可以是别的东西，就是某个函式。那 V 但是U 跟 TV，OK， 这是我们平常在看到的。那我们就把它写出来。那这时候我们看到，哎，里面没有 V 也怎么办？那我们就想说，那如果今天能使用其他的变数的话，那来计算的话，是不是会就是我们这很难算，我们想要用其他的变数，所以我们就来看看底 V 是用什么样的算法来能把它算出来。所以我们就把 V 的函式写出来，写出来以后带回去就发现，哦，它其实底 U 可以写成这么长的式子。那还好它的 P 是常数，所以它变成这边为0的话，我们就会发现 ，OK， 底 U 底 T partial U partial T over at a constant P 这件事情可以把它转化成别的参数啊，别的参数，那 V 跟 T 跟 P， 那你就可以发现，就是说，如果今天这个不能量，你可以量别的，然后把它加总起来。那这个东西是附带的关系啊。我们如果只看这个，我们是很难看到的。但如果今天我们用数学公式的话，我们就可以做到这件事情。好，那好，那接下来so next we are going officially enter PDF 8, sorry, chapter 8 in the textbook. Right, so next one is thermodynamic potential. Potential, actually, potential means the energy related to the position or the state. Okay, so we typically introduce two important energy, also potential energy, called Helmholtz function. Helmholtz free energy gives free energy. We name it F and G. So what are they? Actually, H, F, G function are related to internal energy by using Legendre differentiation transformation. We just introduced that tool for you, right? All the potential function is originated from this equation, du equal to TdS minus PdV. Okay, you know that. So you can see that U is a function of S and V. Okay, so now we regard this equation as z and x and y. So actually, this is the form that we introduced in the Legendre transformation in the beginning, right? So actually, all we need to do is changing the variables. Okay, so you see du equal to partial u over partial s v ds plus partial u partial v s dv. Okay, and you know that this is the slope is t and the slope is minus p. You know that, right? So you see t minus p, okay, and s and v, s and v. So the canonical conjugate is actually the conjugate. Remember that this is kind of, you know, 互格怎么讲？just conjugate conjugate. So you can see that in different material. So the minus PV is a work, right? Related to work. So remember, if we are talking about different material, we may have different work form. Okay, so maybe you can see, you can treat B and N. What does that mean? Magnetic field and magnetization. Okay, and also the electric field and polarization. Okay, you see my P is quite different from the pressure P. Okay, so for the ferroelectric material, so what we do here, although we introduced that as minus P of V, which is for maybe ideal gas, but the concept can be applied to other material, other advanced material that you work in your lab, right? So don't worry about that. So the Helmholtz free energy and Gibbs free energy, that also can be applied to your lab. So we know that internal energy can be treated as a function of S and V. So let's just change U and S, V. So this is the first one, the origin, the starting point. And then we just change one of them as T. So we change that. We change the P here. So we use Legendre transformation by one variables in the previous few page. Or we can say 3. F, T, and V. We just change the first variables, and then the fourth we change both. Okay, G, P, T. So basically, they are all connected. They're describing the same thing, but just changing different variables. What does that mean in our experimental interpretation? Different experimental condition. Okay, so if you measure something at constant temperature and pressure, the energy change in your experiment is measuring Gibbs free energy. Okay, or if you fix the temperature and volume, you measure Helmholtz free energy. But as you can see, the H and U, they're all too difficult to remain constant in your experimental measurements. So the 3 and 4, the third one and fourth one, we pretty like that because it's easier for us to control the experiment procedure. 好，那接下来我们要介绍的是 thermodynamic potential 这个东西。thermodynamic potential 是 F and G， 一个叫做 Helmholtz 自由能，一个是 Gibbs 自由能，吉布斯自由能。OK， 那这些东西其实都一样啊哈。应该说概念是一样的，纯粹就是从 U 这个内能这个地方出发，从这个出发，你可以发现它是 S 跟 V 的函式。那我们把它写出来以后，我们就知道 ，OK， 其实它的 斜率就是我们都知道的一些参数。那这边提及的是，负 PV 大家都知道跟 work 有关，功有关。那这个功其实是因为我们现在修的这个课程其实是比较古早的classical 是比较古早的传统热力学，但实际上各位在各个实验室在研究的非常先进的材料啊，磁性材料啊，铁电材料啊等等的，都有类似的只是不是负 P 跟 V 而已还有自己的例如说磁场跟磁化量嘛然后还有极化量跟电场这些都是可以把它写成同样的 form 同样的格式的 ，OK， 所以还是有用的这学这个是有用的。那接下来我们就可以发现这个 U 是 S 跟 V 的函式嘛，那 H 是 SP， 其实我们就会发现，其实我们只改了一个，我们用李建德 transformation 转换就可以转换其中一个变数，然后 F 的话是转换另外一个变数，然后 G 的话就是把两个变数都转换。OK， 好，那我们就会发现3跟4是我们实验的人最爱的地方。为什么？因为我们可以控制这个 T 跟 P 变成定值。那我们在某个就是这样实验过程中量到能量差距，那其实就是算出来的能量差距就是 G。如果在控温控压下 ，OK， 你的 G 就算出来了。那如果你今天是控温度跟控体积，你的 F 算出来了。那这边就很难你要去控它的 entropy， 超难的吧？那我不知道，我做实验的，我觉得我不是做实验的，所以我觉得这超难。搞不好有厉害的实验可以控 S 我不知道但是就我们直接来看的话，3跟4就是最简单的方式。OK，so if we use the Legendre transformation and then we can summary all these formation into a table. Okay, chapter A in textbook. This is really important table that you can see independent variables SV, SP, TV, TP, and then you can rewrite the things here. Okay, and then you can have its reciprocity relationship, and we also talked about this before by using the mathematic tool, right? And also Maxwell relationship. So all these two we has learned in the previous few PDF too. Okay, so yeah, just get familiar with that. All right. 好，这个表其实就是刚刚的做法，把它全部好好的把它做出来。也就是说，我们之前教李建德转换，然后我们也教了就是互补的关系，还有马克思韦尔关系，这3个都是我们教过的数学的公式、数学的工具，我们把它应用在这里面，你就可以得到这个表。好，那我只能说你就尽力去熟悉这张表吧，哈。Okay, but textbook or other internet, I guess they will they gave us a really nice trick, help us to nice tip, help us to memorize all this table. We say memory squares. So if you have a square, but if you want to use that tip, you need to remember this square first. All right. So VFT, UG, SHP, and the 2 arrows. All right. And arrow 2 is minus, arrow away is plus. So you can see du equal to this T. Okay, U has 2 friends, V and S, right? V and S. U has 2 friends, dV, ds, and the S is arrow away, so it's plus. And V is arrow 2, okay, so it's minus. All right, H is here, and S and P, and S is away, so plus. And P also away, plus. All right, so this is memory square. Furthermore, you can have corner, okay? Corner is this one, that one, that one. SVP. So it has Maxwell relationship. The other has TPS. So this 2 corner has Maxwell relationship. VSP, VSP, TPS, TPS. All right, that's it. 这个不用讲中文吧？这个实在是因为都是英文，所以因为都是 P 啊 ST， 所以讲中文应该也是。总之就是用这个东西去帮助你记忆了哈。好 ，arrow to 就是箭头朝自己的话就是减，箭头离开自己就是加。好，然后还可以帮助你记忆那个角，用角来记忆 corner 角落来记忆马克思韦尔的关系。Okay, so in summary of our question is that delta U is the heat flow, okay, the heat flow for the isochoric reversible process. Remember the CV, right? Isochoric reversible process, and H is CP, okay? So the heat flow, the delta U and delta H is physical meaning is the heat flow in the isochoric reversal process. The heat flow in the isobaric reversal process is delta H. What about delta F and delta G? What does that mean? Okay, so I will explain the answer of these two equations. Okay? 接下来我们就要问呢，就是 delta U 跟 delta H 的物理意义是什么？还记得吗 ？delta U 不是就是 CV 对于温度做积分嘛，对不对？哈，那不做就是 isochoric reversal process 它的改变。然后接下来是 isobaric process， 就是在定压下的改变啊 ，delta H 它 heat flow 嘛，哦，温度改变，然后就看它的 Q 的改变量，然后就是 delta H。那 delta F 跟 delta G 的物理意义又是什么呢？下几页我们会就是跟大家介绍。好 ，the Helmholtz free energy， right， we all know the second law. The second law. Okay, second law is here. Delta S plus delta S naught greater or equal to 0. So you can imagine that we have a system. Okay, we have a system, and we have reservoir. Reservoir is, you can remember that you can imagine that this is a big water tank. So it has constant temperature, and we say, okay, it has delta S. Okay, this is delta S. This is delta S naught. Okay, so for the second law in this system, delta S naught and delta S always increase, all equal to 0 for the reversal process. Okay, so delta S is entropy change of the system. Delta S naught is entropy change of the reservoir. Okay, in the universe, they both increase. Somehow together, they increase. All right, so the reservoir transfer heat to the system. All right, so you have delta S naught equal to minus Q over T. Right, should be okay. And if we put all this here, 0 less than E delta S plus T delta S naught. Okay, we'll just put this here, right? Yeah, at constant T, right? Just times the temperature. And we notice that, okay, this term is minus Q, okay? Because this one, right? So we can rewrite this. It is Q less or equal to temperature and delta S. And then we also know that Q is W minus delta U. Okay, so we just, well, plus. So we just move the delta U to the right-hand side, become this. Right, so now we can name it as a Helmholtz free energy. We define F is U minus TS. Okay, so we can say the W is less or equal to minus delta F, and at constant T, okay? And you see, because this is what we written down, okay? F is a function of temperature and volume, right? So here, a constant temperature. So what does that mean? You can see that this is related to work, okay? The delta Helmholtz free energy is related to work, okay? Then there's one thing we can notice, that this temperature is constant temperature is not that not that strict, 没有那么严重 okay? Because in fact, as long as temperature initial equal to temperature final, you can use Helmholtz function, because the composition of the F is U and TS, right? U and T and S are all past independent, right? Because they are all state variable independent. Okay, so this is not that strict. Okay, 没有那么严重 because U, T, S are all state variable, path independent. Okay, then you can see that delta F is the work done on or by the system in an isothermal reversible process. Okay, isothermal has T initial and T final, right? If the system has no work done or by, which means that 0 greater or equal to delta F E comma V. So which means that A V and F greater less or equal to F I. Oh, you can see that if there's no work, which means that delta F T at constant T and V less or equal to 0. Okay, so F finish. It also tells us, because this is Fi minus F, right? Fi minus FF. So we can just FF minus Fi. So we just put to the right hand side. You can see that FF always less or equal to Fi. What does that mean? It means that it will always trying to decrease. F is always trying to decrease. Okay, even without work. So the condition for the equilibrium is that no change. Whenever Fi and FF equal to each other, they won't change. They become stable. Okay, so that's a really significant, remarkable things that we need to address. We need to put our emphasis on it, because you see, I is always greater than F, and even without the 0, without work. So which means that F trying to decrease whenever I equal to F, which means that they won't change anymore. So it is kind of a measurement that see the material is equilibrium or not. OK， 好，这边要讲的是 Helmholtz free energy。那首先我们就先讲 second law 长这样子嘛，哈，没有问题。那这时候我们就可以假设一个情境哈，就是说这 system 在这里，然后 reservoir 在这里，就是一个热水浴啊，哈，热水浴它会保持温度恒温 然后它会给系统能量哦。那不管怎么样，这个全部的 delta S 是会一直往上的。那好，然后呢，delta S 会写成这样，这没问题。然后我们把这个式子写在这里，然后带一带就发现 ，OK， 这 Q 小于等于 T delta S， 那 Q 又等于 W 加 delta S， delta U。好，然后我们把它放过右边去，我们就可以看到右边这个我们把它定义为 Hamilton's free energy 的形式，然后就可以写成 W 小于等于负 delta F。OK， 那这边的 T 蛮有趣的，因为我们的 F 就是 U 减 TS， 那这个东西它其实是 stay variable， 它不会跟着路径而改变，所以说其实这个 T 没有那么严格，只要一开始的温度跟结束的温度是一样就好了。好，总之呢，我们就可以写出这样的式子。那这时候我们当然了，这就是写完了哈，我们就说 OK， 它跟 work 有关，这个 delta F 其实就是一个 work 在这个 isothermal reversible process 的状况下，所以这一个题目这个答案已经回答前一页的问题了，好的，结束了。但是呢，接下来的事情我觉得更重要哦。那接下来的事情是，如果今天这个系统 P 底 V 等于0，也就是说它没有任何的做工哦，没有任何的 work done or by 哦都没有，也就是说它就是一个安安静静在那里的东西。安安静静在那里的东西0会写成什么样子呢？它0其实是大于等于 delta F 的。OK， 那这是什么意思啊？我们就来解析一下什么是 delta F。delta F 就是 FF final 减掉 FI 一开始的。好，那我们把这个等号就是大于等于，就是移来移去，我们就会发现 OK， 最后的 Hamilton's free energy 会永远小于一开始的 F。OK， 那这什么意思？也就是说，你什么事情都没有去做它也会希望变这样。OK， 那就表示说 F 会一直往小的方向去，即使你没做任何事情。那直到有一天 Fi 跟 FF 会相等了，那好，那你就不会动了嘛。那不会动就表示说它是 equilibrium，reach equilibrium， 到达等平衡状态啊，平衡状态。所以说，如果今天你要去计算一个材料是不是稳定的，你去算它的 different Hamilton's free energy， 哇，那如果它是不变的啊，不变的，没有任何的改变的，那表示说它已经稳定了啊，稳定了。OK， 好，大概是这样。Right, very similar to Hamilton's free energy, Gibbs free energy. Okay, Gibbs free energy is, I mean, we really like that because as experimentalists, right? Well, yeah, because we typically use control temperature, control temperature, control pressure, right, during our experiment, right? So different energy is really useful, especially for phase change for our, well, I mean, material engineering or scientist. Okay, engineer scientist. Right, so let's continue. The Gibbs free energy, Q less or equal to T delta S, right? What we learned here. Okay, so next, we know that Q equal to delta U plus P dV, right? Okay, delta V. If we just put everything here and then we'll push this to the left hand side, we can write that very long things. And then we define the G is U plus PV minus TS. Okay, so this is the definition of the G. Okay, so you see that most of the chemical reaction and phase change are at constant temperature and pressure. I mean, most of the experimental procedure is chemical reaction and phase change, right? And all we perform that at constant temperature and pressure, right? So again, let's take a look. So delta G, this is delta G, less or equal to 0 at temperature and pressure, right? Similarly, GF is less or equal to G I, very similar to what we learned in the previous page. And so you can say dg equal to 0, which means that no gradient, no change at gi and gf. And with g minimum. Okay, so when you has gi equal to gf, well, you see gi always greater than gf and 0. Nothing change. I mean, nothing work input into, and it will try to make it down. Gi trying to greater than at gf. So it kind of going down. As long as the gi equal to gf, which means that there's equilibrium, and equilibrium means g reach is minimum. Okay, so yeah, so that's how we, especially for me, okay, for simulation. The simulation is typically using gift free energy a lot, or Helmholtz free energy a lot, because we just calculate the G, I, and GF, and we can predict how the material will evolve. Okay, I will show you example done by my PhD. I mean, me, by myself, my PhD thesis. Okay, 15 years ago. Okay, I will show you later. So next one. We know that P delta V is the the condition in pressure or volume or temperature. Yes, we know that this is kind of mechanical force that we can see. Okay, we can see in our original or normal condition, mechanics force. But if you are talking about advanced material like magnetic material, ferroelectric material, they may have electrical force and magnetic force, which is non-mechanical force. So in this case, we need to add extra term, which called W. W is non-mechanical, Nm. Okay, so delta G Tp less or equal to minus W and M. Okay, so minus delta G Tp greater or equal to W and M. Okay, so which means that the decrease in the Gibbs function is equal to the maximum energy that can be freed in an isothermal isobaric process and made available for non-mechanical work. Oh, what does that mean? So here, the first part of this sentence answer the question in the previous 2 pages. Okay, the decrease in Gibbs free function. The physical meaning of the Gibbs function is the equal to maximum energy that can be freed in the isothermal and isobaric process. Okay, the available energy that can be used and also made available for non-mechanical work. What is non-mechanical work? Well, we talk about electric field work or magnetic force, or you changing the phases. Okay, so the Gibbs free energy is really useful for you and me. All right. 好，吉布斯自由能很重要。好，那我们就来看看，刚刚这个东西是 Q 小于 T delta S 嘛。好，那我们把连 T delta S 都移到左边去，这边东西会小于0。我们又知道 G 的定义，我们在前面的 table 就可以看到 U 加 PV 减 TS。好，那实际上这边就是 delta G 嘛，对不对？哈，然后那个 delta G 呢，刚刚也说过啊，我们是花弧 T 跟 P 嘛，也就是说我们可以在定温定压下去量它的 energy， 那 energy 就是它的Gibbs free energy 的差值。好，那我们就会发现 T 跟 P 通常都是我们在做实验的时候的状态，我们会固定 temperature， 固定 pressure， 对不对哈？那这其实就是 我们常常在做的化学反应的实验，我们做相变化的实验，基本上都是在 T 跟 P 状态下做的。所以这个 G 对我们来讲是非常的有帮助，非常有用的。好，我们再来看，这写下去 delta G 是小于0的，那又跟前面一样啊 ，GF 会小于等于 GI。那也就是说，你什么事都不做，它就会尽量的把 G minimize， 一直让后面的状态比前面状态还要低，后面状态比前面还要低，跑到最后面哦 ，I 跟 F 一样了，表示说它的平衡了，哦，这就是这样。所以底 G 等于0 with G 的 minimum。OK， 这个我相信大家都可以理解。接下来好，那其实这个基本上就是回答了前面那一句了哈，就这一句前面的问题。就是说 the decrease， 就是give free energy 的下降，其实就等于是它在等温等压下的状态下可以用的最大能量哦，可以用的最大能量。那这个最大能量它会被用掉它，那用掉到哪里呢？它可以去用在 non-mechanical work 上。这个也就是说，如果今天你的材料是假设你可以相变化。那你这个 different 就是可以把它用作相变化哦，就可以把它用在相变化上。那如果今天你的材料是铁电材料或者是磁性材料，那它就可以帮助它做那个极化量的改变。哦，所以其实这个 non-mechanical work 就是不是 PV 啊，不是 P delta V 这一项，我们可以加在旁边。这个东西呢，就是你可以看到这个 delta G 其实就是 WNM， 它可以用的，它可以用。那这个要怎么用？在我的博士论文里面，我就是完全的使用这个式子来去做我的铁电材料的模拟计算。下一页就是这样子。So next, I'm going to give you a really quick example about my PhD thesis 15 years ago. All right. And I hope you can using this application or examples to know that how to apply the concept of thermodynamics into our real world, real research work. Okay. So application of the gift function to phase transformation, phase transition. For example, when an electric field is applied to the ferroelectric material. Okay, so you see here is a microstructure, okay? Initial state. And then you apply electric field. The electric field will try to make, for example, this region, that region, the domains, the region grow because the electric field favor this region. Okay, so they will make this gray area phase transformation into this type of region. Okay, how does it do? The electric field apply and it will make the domain wall, the interface between the faces, move. So you can see applying electric field, it will grow. The interface will move, all the interface will move, and then eventually become one type of domains, okay? Or we can say twin. Right, so reach equilibrium state. Equilibrium state, okay? So you can imagine that electric field is non-mechanical work, right? And the non-mechanical work apply, which means that it has more available energy, gift energy available, and then the gift energy will be used to move the domain wall to achieve phase transition. Okay, so the gift energy can be written down like this: Gu plus Pb minus Ts, of course, but minus EP. So now you know this is non-mechanical work. So here is electric field, and this is polarization. Okay, I guess some of you study in ferrometry material, so then I guess you will understand what I'm talking about. Okay. In other words, this can be written down Q equal to delta U plus P dV minus E D. E. Okay, and of course it calls WNN, non-mechanical force. Work. And minus delta G T comma P less or equal to minus E D P. And of course, this is called WNM. Okay, so now I just give you an example that this equation introduced previous page, how to write it down for ferrometry material. Now, this stuff is difficult. Don't worry. This is my thing. Okay. This is my thesis. So what I'm thinking is that all these available non-mechanical work will be used to move the interface. How to measure the interface movement, how the dissipation that they move the domain wall. We write down, I don't know, it's like per C. The per C is actually summing up all the domain wall. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I mean, just summing up together. And each of the domain wall can be written down as mobility times velocity divided by half. What does that mean? Half mv squared. Okay, half. This is m. This is m. V squared, the velocity of the domain wall movement, and all the area times area. Okay, so all the energy should be used. All the energy should be used into moving the domain walls. Okay, so turned out I can use that to simulate this. Okay, I will see you after 20 minutes, and I will continue to translate this and also give you a video. Okay, thank you. 哎，现在学生翘课越来越严重，有在 care。我想请问老师，就是我还要再改我的，因为好像周老师跟鲍老师没有那种要求。这倒是哈，就不用了。还有就是这个空白出现的就对了，就这种。哎，你有没有？可是，哎，你有没有论文比对？对啊，就是论文比对，那不用比对啊。C，哎，但是我觉得很多很奇怪的地方，例如他把我的标题的一大部分就是说跟培德学长论文一模一样，那问题是就是那没办法改，就是说在今天说改成那个 different railway，没关系啊。这个好像给系主任签，就是系办啊。OK， 就目前先这样。好 ，OK， 谢谢老师，谢谢老师。好。 页就是我把吉布斯函式应用在我那时候写博士论文的时候，大概是15年前啊。然后我那时候就是在模拟铁电材料的微结构的演进。好，那铁电材料它蛮酷的，就是它只要给一个电场，那个电场的方向会决定它会喜欢哪一些区域，它们叫做 domain， 好，可能中文叫筹域吧，哈。那这些 domain 就是例如说刚刚的电场，它可能会喜欢这一种形式的微结构，它就会把它其他的灰色的部分吃掉，吃掉。那这个吃掉怎么吃呢？它用筹域臂 domain wall 去移动，去把它吃掉它，到最后变成这样子，变成 equilibrium state， 就是叫什么？就是等效，叫做平衡的状态。那这个就跟我们的 give free energy 是非常相关的哦。我们可以把刚刚写的这个式子的 non-mechanical 的这个位置，把它改成 electric field 乘上 polarization。OK， 那实际上基本上这一个东西就是从这个式子变来的，而且这边右边的 E 底 P 就是我们的 WNM 啊 ，WNM 就是不是机械性的功啊，不是机械性的功。好，那这样子写出来以后，到最后就可以写出 OK， 负 delta GTP 是小于等于不是机械性的功。OK， 那不是机械性的功呢，就是电的功嘛，电做的功，电乘上它的极化量改变量。OK， 好，那这时候我们就可以看到，这个就是电场加下去，它就多了能量，那些能量是 non-mechanical work， 它多了能量就会被用在，这 give free energy 就有了嘛，它就是可以用它 available， 它可以让它用。那这用在哪里呢？ phase transition 相变化。其实这个筹域臂的移动就是一种相变化，它把这边的相变成这边的相，对不对哈？好，那所以说我们就来看这个筹域臂的移动。dissipation rate 的当然就是这是这里不用管哈，这是不用学，它纯粹只是一个我们的计算模型的一个表示方式。它要把那个能量用在移动筹域臂，那这个筹域臂要怎么去计算它的能量移动的能量呢？需要耗损的能量，其实就跟你要推动一个物体是一样的道理，1/2 mv 平方。那这个 m 就是它的质量嘛，对不对哈？那在这里就是这个墙壁这个 interface 的移动的难易度，越难就很像是质量越重，是一样的道理。所以是1/2 mv 平方。当然了，这个面越大，当然就越难移动；越小就越难移动嘛。所以你必须要跟底 A， 就是它的面积有关系，加总起来就会是移动所有筹域臂的能量。那这个能量就会是你的电场驱动它的功造成的。Okay, so after we form all these formula equation, I can write down a program by MATLAB. Okay, so I wrote a MATLAB to predict the hysteresis loop of the ferroelectric material. Okay, so this is the all right. So you can see that at the beginning, okay, at the beginning there has a lot of domains, and then after the electric field, it will make the domains eat other. You see? 那怎么弄啊？ So you can see the interface changing, moving. I just calculate all the electric field times the polarization. So it's kind of available work, available work, and then use that to move the domain. So when the domain move, I just make the work minimize. So it will go to try to minimize the energy so I can predict the movement of the domain. And after the movement of domain, we can determine the material property at the left-hand side, and which can be measured by experiment. Okay, so you can see the left-hand side is experiment, and the dot is the result I predict. So you can see that it moves, and electric field change the direction, become the pink, and then change direction again, become red again. So you can see that that's how I use skip free energy to help me to graduate, obtain my PhD degree. All right, that's it. 听得懂吗？就是大家都知道电场会让他选择他喜欢的 domain 嘛，那所以我就使用 MATLAB 去计算它的能量 ，skip free energy 能量，然后把它用在移动这些 domain wall。那移动多少，我就把这 skip free energy 减掉，然后变成最小化。那所以我的 energy 一直在变，因为我一直在 apply 我的电场越来越大，所以它就会一直去推那些 domain wall，就把它推到全部都是红色。然后呢，接下来转向了，电场会越来越小，然后转向变成负的，它就变成粉红色。所以你看到这些微结构的变化，然后变过来变过去这样。那它的材料参数把它总体的计算出来以后，就会跟我的实验的现象会是非常类似的。OK， 然后我就毕业了，好啊，就这样。All right, so that's how the skip free energy helped me to obtain my PhD degree. Okay, that's the reason why I can stand here. Okay, I'm really grateful. Thanks, skip free energy. Next one, energy. Well, you all know energy has three types. The first one is kinetic energy, the other is potential energy, and the other is internal energy. Internal energy is actually why the material is here, why the material existing in this world. Okay, so internal energy, well, everyone is an energy. We just another form of energy. Wow, this is kind of philosophy. Okay. And kinetic energy is associated with motion. If there's something has motion, movement, displacement, translation, rotation, it has kinetic energy. Potential energy, on the other hand, is something that if you put at that stage, at that status, they has their own energy. And if the condition change, the potential energy may released. For example, just like this. You put it in the cliff. The rock is at the cliff. And then if it fall, potential energy decrease. But you notice that the potential energy and kinetic energy can be transferred, can be switched. Because if you have losing your potential energy, you will have more kinetic energy at that time. All right. 好，能量有三种，一个是内能，内能就是有点像是你自己为什么会出现在这个世界上，你本身就是一个能量的另外一种形式。我们大家都是有能量的人。好，那蛮哲学的。那接下来是 kinetic energy， 就是你动态旋转改变。那接下来 potential energy 不一样 ，potential energy 就是你放在某个部分某个位置，你不动它，它就是含有这个能量。那当它掉下来的时候，当状况改变的时候，它可能这些位能会释放出来，释放出来，然后它就可能会转换成动能，然后就会有比较快或什么之类的。讲到这个，我觉得我最近看事情就会，就是现在题外话，就是聊聊天就是我最近看事情，我就觉得说，也觉得是越老越怕死，所以我每次走在路上，我看到有高的东西。大的东西，气瓶，我都会我都会有自己的这种惧怕感。为什么？因为它有能量，它有位能啊，对不对？你看这高的东西它就是很高嘛，它就有位能啊。所以也就是说，只要在有能量很高的旁边，前方高能，我就会很害怕。就例如说，车子很快，它也是一个动能很快的东西，我也会觉得很害怕。然后外面那个常会有那个码头不会有气瓶嘛？每个气瓶都是高压嘛，压在里面，所以它能量很大。所以我看那个就是一大堆大能量在里面。其实炸弹也是啊，炸弹也是蕴含很多能量，对哈。所以实际上对我来说，这些对我来说都是炸弹。所以我每次看到我都会 的赶快跑走，就是不要待在它旁边。所以我绝对不会在高压氧气瓶那边就是打电话啊。我常看到有同学在那边打电话啊，然后但在高压气瓶那我就哦好恐怖。虽然一定是安全的啦，但是不小心来个失误，那个它就会爆啊或什么之类的，所以哎我都会很害怕。就这样没事啊，大家要小心。Next, let's talk about chemical potential. What is chemical potential? Chemical potential is that we are going to discuss from the closed system to open system because now we're going to the more complicated case that the container is opened. So atom can freely change their position and go out to the container. So which means that their position changed. So their potential will change. All right. So dn kilomoles, of course, the change of the mole, change of the mass of matter are introduced into system. So you see that it is with its own internal energy. Internal energy. Okay, so you see that as we mentioned, everything is sitting on in the wall, which means that they has internal energy. So if you something leave this system, of course internal energy will decrease because you're missing something. Yes, the internal energy is gone. All right. So they has their own energy. If they change the mole, change the mass, internal energy will change. And then the added energy can be written. So if you adding something into the system, of course you are adding some internal energy, and also they has the potential because each atoms may has an interaction. So added energy can be written as mu dm. Mu we call chemical potential. So, and then we are going to discuss this in more detail later. All right, so for example, if you have a particle or atoms here, all right, and then you're adding another atoms here, all right, and their distance, we call R. We call R. Okay, so the potential energy V can be written in this form. Okay, V is the potential energy. VR is a function of R. The X is distance between the two atoms. So it will always look like this. Okay, it's called potential landscape. And this is called potential well due to the intermolecular forces. Okay, so you can see that at this distance, their potential energy will be the minimum, which means that these two atoms prefer stay within this distance are known. Okay, perfect distance. So just like people, just like human, right? We have, comfortable distance, safety distance, okay, between each other. Right. So if it's too close, it will increase their potential. So two people too close, they will too close, they will, fight. But if you're too remote, you cannot feel anything, right? So there is a most perfect distance between two atoms, just like human being. Okay, So we can have a conclusion that when we place two particle, you can say particle or atoms. Okay, when we place two particles r equal to infinity, if the r equal to infinity, which means that you haven't put it that yet. Okay, it's out of the system. K equal to 0, no kinetic energy, of course. They didn't meet. They haven't met. Okay, they haven't met. Sorry, they haven't met. V equal to 0, E equal to 0. Okay, E is your total energy. But if you put it into the game, into the system, when R equal to R naught, K minus V. I mean, if you put the atom into the container, there are some total energy there. Okay, and then total energy equal to K plus V gamma. So you can see that the energy is there, and they can transfer from V to K, as we mentioned that the potential energy can transfer to the K. So at that time, at the R naught distance, actually the energy well depth equal to the K, the K here. Okay, so you can imagine that this is the energy they have. If they put here, they are totally fine, no energy transfer. But if you put to here, I mean, it will generating the kinetic energy, push it back to the minimum. So you have the potential energy will swap between potential energy and kinetic energy, transform to each other. Okay, when due to the different position. 好 ，chemical potential 其实就是一种你把东西加进去把东西加进去的一种改变。那改变加进去，当然会改变它的质量。质量就是用 kilomole 来表示。而且每个东西都有自己的内能，所以你加进去一定会加能量进去。好，那我们就想象有两颗分子，两颗原子或是球放到系统里面，那它们之间的距离是 r。如果你一开始没有放的话，放超远、无限远，比如说它根本没放进去嘛，所以根本就没有任何的能量的改变。但是当你一旦放进去以后，它们之间就会有能量。那这个能量呢，会互相转换，会转换成要么位能，要么动能。好，你可以想象这个位能的最深处，其实就是它的动能的大小转换过来的。如果你今天把它推到不是最稳定的距离的时候，它就会产生动能把它推回去。OK， 当然是你可以想象越靠近它，就会越大的排斥力，然后它的动能就会越大。OK， 所以你可以想象这个 depth 这个深度就会是它的 K 减掉 V R naught。OK， 好，那基本上就是这样。总之就会有一个最适当的距离给两个 atom 就对了。All right, so let's continue our lecture to chemical potential. So imagine that you have the sulfuric acid plus into the water. Okay, pour into the water, and of course you imagine that the temperature will increase. As you can see, the temperature increase means that you're adding some energy into it, right? And this is 10 to minus 5 kilomole, and this is 10 to minus 2 kilomole. Oh, very small amount, a relatively big amount. And CP and C water, the CP water, CP acid has this value, and you can see very big amount, small amount. So you can imagine that, okay, greater than 10 to 3 order, 1000 times. So you can say, okay, it's greater, much greater. All right. So now Q heat gained by the water equal to mCp delta T, no problem, right? So mCp delta T. So heat gained by water is 5.56 times 7.52 times the temperature change 0.1 equal to 418 joule. No problem. Okay, so this is straightforward. How about for the acid? For acid, okay. For acid, the mu here equal to Q divided by delta N. As we mentioned, mu times dN is the chemical potential times dN is where is it? Here. The chemical potential mu times dN is the added energy, right? So the added energy gained by the water must be 418 joule equal to mu times delta N. Okay, so we can say, okay, 418 divided by 10 to minus 5 equal to minus 4.18 times 10 to 7 joule kilomole minus 1. Okay? Because heat transfer from acid to water, mu is negative for acid. Okay, so that's the statement I'm going to say here. All right. Chemical energy per particle. So this is a 1 kilomole, right? So mu divided by 6.02 times 10 to minus 26. Minus 20, sorry, not minus 26 only. 26. Because 26 is kilomole. Okay, kilomole. You need to add in more, 3 more order. Minus 6.94 times 10 to minus 20 joule, or minus 0.43 electron volt. What is electron? I mean, 1 electron is kind of the energy electron volt. It's kind of unit for energy, but it's too small. So it's better for us to write down a electron volt has the proper amount for describing such tiny energy. Alright， 好，我们继续讲，就是说我们有一个例题哈，加了一个酸进去到水里面，而且它相对来讲是比较小3个 order 的质量，所以我们就可以说它是远大于了哈。好，然后 CP 是多少 ？CP 的 water 跟 CPX 是多少？然后 T 基本上是就是上升0.1度。好，那我们就可以知道，在水里面得到的热总共是 mCp delta T 算出来418 joule。那但是如果是看酸的部分的话呢，酸 nu 乘上 delta N， 其实在前面就有说它是加进的能量是多少，所以是 mu 乘上 delta N 等于 Q 嘛哈，所以我们就把418除上10的负次方，就得到这个式子。那这边为什么写一个负呢？是因为heat 就是热是从酸传到水里面去的，所以 mu 在这里是负的 ，acid 的话，酸的话它是负的，因为它把热传到水里面去了。好，然后接下来是它自己少能量，然后接下来我们就要看 chemical energy per particle， 就是刚刚是1 k mole kilomole 1000 摩尔的能量嘛，好 mu 好，那如果是1颗的话呢，那我就把它除以6.02乘10的26次方，26次方就是23再乘上10的3次方嘛，哈，因为有1000，所以你可以得到这个数字。这数字呢太小了，负20啊，哈，那因为它太小，我们就科学家就想出了另外一个叫做 electron volt 的能量，哦，把它变比较小，那就可以写的比较不用写那么多10的负几次方这种的大小，比较适合去估算 mu 这个值。Okay, next, particle in an open system. So if you has a system adding one type of particles, just one types, okay, one type. So you can say, here, mu dm, right? So your internal energy increased because you adding something, and the change that energy is mu times dn. We wrote it in page 8. Remember that? So now your U is a function of S, V, N now in the open system. Previously, you don't have N because you have closed system, but now you have open system. Your kilomole will change. Okay, so again, we can write it down in the differentiation form with a slope, right? So the first one is temperature. This is minus P. This is nu. Okay, so nu is a partial V over partial N at the constant entropy and volume. So this is adding one type of particles. How about many types? Many types. Well, not that difficult. N types. Okay, sorry, I missed one word. So just like plus mu dn, but now you have many types, n types of particle. So j equal to 1. And this is m, okay? And this is mu j d n j. Okay, so you have 1, 2, 3, 4 to j, and the maxima is m. Okay, so yeah, just m1 dn1, m2, so not m, sorry, mu1 dn1, mu2 dn2, mu3 dn3, blah 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 blah, mu m dnm. Okay, so just sum it out together, all of them. So all you need to do is adding them, and then now mu j equal to partial u over partial n j at constant s and v and m k. Okay, this k is a little bit, you need to be a little bit careful. The k here is the rest of n, not only one. Okay, this is n. If you are talking about mu1, the nk should be n2, n3, n4, n5, n6, blah 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 to mm. Okay, so this is a rest. Be careful. 好，我们现在要讲就是在一个开放空间去加颗粒、加原子或分子，加进去，总之它的内能就会提升嘛，因为本身这个材料加进去的东西自己就有内能，你加上去当然内能提升咯。所以 nu times dn 是它的改变量。那我们就会知道我们的 internal energy 内能会变成 entropy 跟 V 跟 N 的函式，当然就可以写成有斜率的式子。那我们就可以知道我们的 nu 就会是 partial U 和 partial N at constant S 跟 V。OK， 好，那是一颗的。那我们现在加很多颗 M types 颗啊，很多颗，很多种啊，很多种。那这很多种呢，我们就可以发现 每一种都加进去的话，都会是 n1 乘上mu1 乘上底 n1，mu2 乘上底 n2，好，这样子依此类推，那这样就把它加起来就好了，哦，没什么问题。那当然，我们的 μj 就会是 partial u over partial nj sv 是常数 ，nk 也是常数，这个 k 不是只有一个哦，它是剩下的哦，剩下的哦，剩下的，所以它有很多个。也就是说，如果今天是 n mu1 的话，n1 的话，这边就是 n2、n3、n4、n5，哒 nm，所以这边其实很长的哦，这边其实超长的，我只是写的比较少一点，小心一点。All right, so now you can see u now is the function of SV and n1, n2, n3, blah, 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 nn. So we want to using some mathematic tool to help us to get more information, more underneath relationship in this formula. Okay, we notice that they are a extensive property. Extensive properties. Did you notice that every variables in this formula is extensive property? If you increase the mass, you increase entropy is increase, volume increase, n1 increase, n2 increase. Okay, so which means that you increase mass, everything increase. So which means that it is extensive property everywhere. Okay, in this form. Okay, so which means that if you times a multiplier like lambda time, okay, so lambda u equal to u lambda s lambda v lambda n 1 lambda m2 lambda mn. So you can say everyone increased by lambda times still hold this relationship. In the mathematic term, we call that homogeneous function, 均值函数. Okay, and then we name this equation 1. 1. All right. So now there's some trick we can do for the equation 1. Differentiate the equation 1 by lambda. Let's do it. U equal to partial u partial lambda partial s partial lambda s partial lambda plus partial u partial lambda v partial lambda v partial lambda. Then partial u partial lambda mn partial lambda mathematician is so smart, I would say. Who can think about that? It's just genius. Oh my God. Okay, so they did the differentiation for homogeneous function. So it differentiated by lambda. Okay. Differentiate by lambda. Okay, lambda u here, and lambda s is and they time together, right? So you need to differentiation the first term and then times differentiation for the next term, right? So partial u times partial s. Okay. So you need to differentiation itself, and then you differentiate it by itself. Okay. Oh, so I guess you can understand what I'm talking about. Okay, you need to differentiate u first, and then you differentiate itself. All right. So it looks like this. Why we should do that? Because the mathematician to think about why not just then set lambda equal to 1. Wow. So it become 1. And this become 1. And here 1. Okay. And then here is here is S. Here is V. Here is M. Okay. So everything become clear and simple. So this is called Euler theorem for homogeneous function. Also, Euler is really a genius. Okay, who think about this? So you see, U equal to S times partial U partial S plus V times partial U over partial V. Okay, and then the rest of it can be written as here. Very smart. And you know that this is temperature, and this is minus P, and this, right, is mu J. So U equal to ST minus PV plus sigma M J equal to 1 mu J NJ. All right. So this one can, make two conclusions. The first one is that if you know that G equal to U minus ST plus PV, so actually G is M J equal to 1 mu J MJ. Okay, so when you have a closed open system, you're adding something. It also can tell us the Gibbs free energy also be changed. Okay, available energy is changed, of course. Then another thing is that if you compare okay, so you can do differentiation du. So this is TDS SDT from here, and minus PV to do the differentiation. You can get this one, and here we can get that one. So now we have two informations. All right, and then we will use this one later. All right. 好， 我们先要讲了哈，就是我们都知道加了很多种类的 M-type 原子，哦，它的 U 的函式从此以后变长这样子。好啦，那我们就会仔细的看，发现，哎，这里面的所有的 parameters 都是参数，都是 extensive property，也就是说，它跟质量成正比。也就是说，你质量越多，它也会变多，质量2倍，它就变2倍。所以说这边全部都是哦 ，U、S、V、N1、N2 都是，质量越多就会一起变大。所以说我们就可以乘上浪打倍。那反正大家都会乘浪打倍，都一样嘛，对不对？好，那当然这个等式会成立。所以这你就会发现，你如果乘上一个浪打在外面，会等同于每一个参数乘上浪打倍，所以这个叫做 homogeneous function， 在数学上。好，那这时候尤拉就想到一个超聪明的解法，他说我们就把这个式子哈 differentiate 浪打。好，我们 differentiate 浪打，这时候因为它是 u 嘛，我们要 differentiate 它里面的东西，所以说这当然是 differentiate 是没问题，但是这是 u 的函式，你要 differentiate 浪打，你必须要，而且每一个参数都要 differentiate，所以说你会先 differentiate u 以后，再去 differentiate 里面的单一的参数，然后每个都这样做，所以就会变成 partial u 除以 partial 浪打 s， 然后 partial 浪打 s 除以 partial 浪打 ，OK， 然后继续以此类推。而且它最厉害的地方是，它把它设浪打等于1，它设定浪打，谁说浪打不能等于1的？可以耶，然后就浪打等于1，结果就把这个式子重新写成这样子了。然后我们又知道这边是 t， 这边是 minus p， 好，我们就可以把它写成 u 等于 st 减掉 pv 加上 sigma mj μj nj， 结果我们就跟 g 来比，我们就会发现哦，原来 g 其实就等于这一项哎，就是这样而已。好，所以得到第一个结论。第一个结论纯粹只是把这个式子写成底的形式而已了哈。就把底 u 写出来以后，这两个式子就是这个的微分，这两个 term 就是这个微分，这两个 term 就是这个的微分。等一下我们会继续用到。Okay, next. So we are going to introduce the famous Gibbs-Duran equation. Okay, so this is the equation we just obtained in this page, right? But we also know that the definition, by definition, du equal to TdS minus PdV times this one. So always we just need to compare a little bit. We compare and then we know that, oh, S dt minus V dP plus sigma m j equal to 1 nj d mu j equal to 0. Okay, and mostly in our experiment, or you can say give free energy condition, okay, if T and P is constant, then sigma m j equal to 1, nj d mu j equal to 0. Oh, so which means that if the temperature and pressure is constant, no matter how you add in this this one always equal to 0. Interesting. So this G we obtained in the previous page, right? And we write down the change of G. Change of G equal to this one and that one, and this one equal to 0. And then we can obtain the famous Gibbs-Duran equation, dg Tp equal to sigma m j equal to 1 mu j dnj. Okay, so this is the famous Gibbs-Duran equation. And well, to me, it's a little bit, you know, straightforward. What do you think? Well, you can see that you're adding something. You're adding something. And then, of course, adding something, you introduce more energy into the system, which means that it can be used to do the work. So this is very straightforward. All right. 好，我们介绍是有名的 Gibbs-Duran 的方程式。我们前一页不是推导出这个东西吗？那我们又有知道就是介绍 chemical potential 的第一页啊哈，我们写出这个东西，我们来比较一下，就发现它剩下这些项，而剩下这些项的时候，我们接下来继续看，在一般的做实验的状态下的话，温度跟压力不都是几乎都被我们控制住为等于是常数吗？所以我们就会发现，如果在这样的状况下，我们得到这个等于0，那这时候这个等于0，我们的 G 长这样子。如果我们的改变 G 会变成，如果做微分的话，前面跟后面嘛，那后半段你就可以发现它是等于0的。所以就是说，这个底 G 啊，这底 G 在 TP 的常数下为常数下的状况下，这个就是它的 give free energy 的改变量。我觉得这也是蛮直觉的啊，就是当你一个东西加入了新的东西，你当然就是给它一些能量，那些能量就可以被它用在不同的地方啊，例如说像转变啊，例如说去做其他的化学反应啊，就是它 G 就是它可以用的能量嘛，你加入东西进去，它当然就多能量起来，让你去做别的事情，还蛮 straightforward 的啊。All right, next one. 3 minutes. 加油。Next one, phase equilibrium. Because we talk about equilibrium, we talk about give free energy. So typically, we're going to minimize the give free energy and to see if the material is equilibrium or not. So now we're going to see phase equilibrium. So now we has a container and a material in a controlled condition, and it has two phases, phase A and phase B. Each phase has TA, PA, VA, UA, NA, TP, okay, etc. So again, no heat flow because this isolated, and no work down. Just put that and make it equilibrium itself. Okay, so now we see they need across this interface, they need to change. It need to swap the material, right? But because they are all in the same system, nothing added. Okay, so which means that across this interface, conservation of mass must be held, right? The NB equal to minus the NA. So if you have the phase become A, or if you have phase A become B, they need to be exactly the same number and opposite side, right? Conservation of mass. And conservation of volume, of course, volume is fixed. So minus dVA equal to dVB, no problem. Conservation of energy, of course, the energy won't change because it's closed system. Okay, now just try to let you know this is minus sign because they have opposite side. Okay, of course, the SB equal to minus the SA. Again, minus sign. So the S equal to the SA plus the SB equal to 0. Okay. I will draw it in blue. So now we know that U equal to TDS, the U equal to TDS minus PdV mu dN. Okay, so we have two phases. We always can write the UA and the UB. what to do about this. We sum them not together. And we can obtain blah, 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 blah. All right. Of course, you can see that this is at page 18. All right. So I will see you after 10 minutes. If you have any questions, just come here. Yeah. Have a nice break. Welcome back. 我发现，我准备就上课准备，今天准备太少了，就是剩下的从20页到最后的30几，就剩下的10页，我没有先看过。也就是说，我等下就是会临场就是看着我的小抄，然后来讲解，所以有可能会比较不顺，然后那个逻辑可能会不太通顺。因为我每次上课之前，我都会先看过一遍，然后确保知道这个逻辑是什么，这样。那所以讲起来就会比较有自信一点嘛，哦，然后有自信的话，你们也会比较就 get 到我在讲什么。但是如果今天是我当下就是看到这个就讲这一部分，看到那个就讲，如果没有好的顺序的话，你可能会比较所以等一下抱歉哈，等一下可能这一页之后可能会有那种现在要讲什么，这种可能需要有一些时间呃来反应一下哈，所以等一下就大家就是多多见谅。好，那我们就继续开始。All right, so let's continue our lecture. We just talked about a material at the, at a very close to system, but there's an interface between each other and no heat flow, no work down. So it's just put there, let it reach its own equilibrium state. Okay, so across that boundary, it must obey conservation of mass, conservation of volume and energy, because no mass, no energy, no volume changed in this entire material. So across that boundary, the change NB will need to be equal to change NA, but with minus sign, opposite sign, and like V, like U, like S. So we know that ds equal to dsa plus dsb equal to 0, of course, right? Then in page 18, we can write down du equal to this one, db, ub that equal to that one for both sides of the material, face A and face B. And sum that together, it becomes this one, and that one. No problem. Okay? Now, let's take a look. Again, similar to our method. Okay, dua, dva, dna, right? The dna and dva and dua can be any value. Remember that value. The change of the value can be anything, but they need to sum them up, minus them, and equal to 0. Any value. So which means that there is only one possibility for this is this need to be 0. This could be 0. This need to be 0. Only in this condition, this equation always held. Okay, so you can see this one, TA equal to TB, reach the equilibrium. PA equal to PB, reach the equilibrium. Mu A equal to VB, reach the equilibrium. All right, so that's the idea. So everything equal to each other become equilibrium. 好，这一页就是在讲说一个材料，它有两项，这两项中间当然有个 interface， 一个界面。当然，经过这个界面的传输一定要对等的、相等的，不然的话它就会能量啊、体积啊、质量啊就会改变，这不对吧？ 就放在那边让它平衡，怎么可能会多质量哦，对不对哈？多能量等等等，所以说，然后它的 entropy across 就是通过这个界面都会是一样的。好，那写下这个以后，这是我们已知的条件了，没有问题。但是第18页告诉我们，dUA 会等于这个东西，dUB 会等于这个东西，也就是说，这两个部分都必须符合这个第18页我们自己写的式子。那写了以后，我们把它加起来，我们就移动一下，就会发现长这样子会等于0。好，那这时候我们就会发现 dUA、dVA、dNA 这都是改变量，改变量可以是任何值哦。那改变量任何值，只有一种解决方法，就是会让它们全部加总起来或加减起来会等于0。只有一种方法，永远都会成立，就会是前面的系数为0。那这样子的话，就可以看得出来，当你要达到 phase equilibrium。你一定要温度相等、压力相等，还有一个更重要的是 chemical potential 相等。OK。Next, we are going to go for a more difficult part. We want to go before the equilibrium state is reached. Just one step. One step. After that step, your equilibrium state reached. Okay? So this means that the system is during the process, right? Because you're going to go to the equilibrium state, just one step away. Okay, so the delta S equal to delta SA, delta SB greater than 0. Previously, equal to 0, but equal to 0. But here, we're going toward the equilibrium state. So this becomes greater than 0. Okay, so let's imagine that if the phase interface, okay, has just one step reach the equilibrium state. So what is it? What is that state? NA and B. Now it's NA plus delta NA. So from A to B, we say mass flow. Okay, when the phase A mass flow to B, it reached the equilibrium state. Okay. Yeah. The remaining part, they already reached the energy, the equilibrium state. No problem. All right. So now, as we see, you see that the UA equal to 0, the VA equal to 0, and the UB equal to 0, the VB equal to 0 because they are already reached the equilibrium state. We only have one step, change the mass, and then we reach the equilibrium state. Okay, so this one already satisfy the condition. Okay, so now delta SA, delta SB here greater than 0. What is delta SA? Mu A times minus delta NA. Where does it come from? Yeah. So you can see the delta UA, UB are all fixed. VA, VB fixed. So you can see that the only two things left is TSA, mu, dN. Okay. So here is something left because they are all 0 now. Okay. So delta SA, delta SB, they come out together, need to be greater than, sum out together become greater than 0. So what will it be? Equal delta NA divided by T mu A minus mu B greater than 0. And then, luckily, we will see mu A greater than mu B. Wow, which means that if your mass flow is from A to B, so which means that the mass flow is going to from higher mu to a lower mu, and then you will reach the equilibrium state. And you can do exactly the same procedure, and then you will find that, okay, heat is volume to higher pressure to lower pressure. Okay, this is really interesting a way to see how the properties flow to reach the equilibrium state. 好，这一页跟上一页非常相关，上一页是已经等于0了，但这一页是还没有等于0，你要往平衡的方向走。好，那这时候我们就假设其他的都已经稳了，其他的都已经达到平衡了，就只差一步啊，就差一步而已。什么一步？你的质量要从 phase A 移动到 phase B， 就这么一步，移动完以后就平衡了。好，我们就假设是这样子。那我们来算算看会怎么样。那这时候就差这一步，也就是 NA delta NA 要变成 delta， 变成到 B 那边去了。所以说 NA 加 delta NA 的 NB 减 delta NA 了哈。好，那这时候如果以前面这一页的公式来算的话，你会发现，UA 跟 UB 都已经为0啦，你已经达到等效啦，不达到平衡啦。然后 VA、VB 也达到平衡啦，只剩下这2项。好，那我们就把这2项写在这里，噔噔噔噔噔噔噔噔 ，OK， 写下来了。然后我们就把它加在一起看看，结果我们加在一起发现，加在一起要大于0啦，哈，加在一起要大于0。那做完以后，我们就会发现，哦 ，μA 大于 μB， 也就是说，在这个状况下 ，A 流向 B 的意思就是，其实因为 μA 大于 μB， 也就是说 ，mass 质量会从高的 chemical potential 的地方流到低的 chemical potential 的地方。好，那这就是你的结论。如果你今天把这个东西换成是 volume 这样流过来，那一样做法，你会得到 higher pressure 等于 higher pressure 会往 low pressure 体积往那边走，那温度也是温度就会从高热的流到低温的，就这样。好，那还蛮酷的。All right, next one, I will go to next topic called the Gibbs phase rule. Okay, well, just related to the phase. Okay, if you have a constituents K and pi phases, so if you have such many materials, different material, okay, and each of them has pi systems, okay, pi systems, phase system. For example, you have tetragonal, rhombahedral, blah, 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 blah system, all right? And with temperature, phases maybe gas or liquid or solid, okay? So they have pi systems with temperature and pressure fixed. The condition for equilibrium is mu I1 equal to mu I2 equal to mu I pi equal to each other, because all the chemical potential need to be equal to each other, and then you reach equilibrium state, right? So, which means that you have how many degree of freedom? Let me take a look. Oh, right. Sorry, I didn't prepare this. Okay, but I will try my best to make it as fluent as possible. All right, so now you have temperature, pressure fixed, right? So which means that experimentalists can choose the value. Okay, so you have 2 independent variables. 2 independent variables. Okay, And the independent variable means that you can choose either temperature equal to 300 K, pressure 1 atm. Okay. This also called the degree of freedom. Degree of freedom, which means that the human being can choose freely. Okay, so we call it DOF. DOF. Okay. All right. So I use yellow. Okay, degree of freedom, temperature and pressure is fixed. However, because this is a material, the material has their law or rule to obey. What does that mean? If you have an equilibrium state material, if you have such many particles, materials in that material, in that system, and also each of them may have high phases. Okay, so you can imagine that in the previous case, your previous case you only have one constituent, two phases, phase A, phase B. Okay, so if you have many constituent K and pi for each phase system, you will have mu I1 equal to mu I2 equal to mu I pi. So they need to be all the same to reach the equilibrium state. So you can see that here, one equation side, right? So it's equation 1. And there is equation 2. And there's this equation pi minus 1. Okay? You have pi phases. So this is one phase and second phase. This is equation 1. So you have pi minus 1. So you see in each constituent, they have pi phases. And phases provide pi minus 1 condition. You need to fit, you need to satisfy pi minus 1. But you have k constituent, k type of materials in this system. So these k pi minus 1 equations. Okay, we can also call this constraint. The constraint I use blue. Okay, so now this is phases, but there are many K materials in this in this system, right? So each of them need to satisfy another variables, because you see you can add in whatever you want in this material in this system. For example, you prefer more materials, like more Fe in this system, more Al in this system. Okay, so you can choose the more concentration. So the concentration need to be can choose by human being. Okay, so you can see that K and times pi phases. Okay, pi.呀，这什么意思啊？我有点忘记了，对不起。The molar fraction，molar fraction 就是所有的K 可以是你自由的选择，对。 看一下啊 ，K 派的 degree of freedom。哦，每一种摆在哪？刚每一种项跟每一种材料，你都可以自由的选择它的比例。Okay, so you can see that as an experimentist, you can choose whatever composition you like, right? And choose whatever phase you like. So this is also the degree of freedom. K pi degree of freedom. The degree of freedom. Okay? Because this is your material. You whatever you like, you just choose that, and then you can just make it. All right. So you can have degree of freedom. K pi. You can have K whatever how many material you want to add, and you also can choose each of them has its own phases. Into put that into the system. But these molar fraction need to has another equation to constrain that, because those sum of the fraction is 1. Okay, so you need to be something about as 1. And also you have pi phases for each material. You need to satisfy one fraction 1. So you have pi equations. Okay, need to be satisfied as 1. Then you see that you have number of degree of freedom 2 plus K pi, and blue one is pi plus K times pi minus 1. And then sum that together, you can get F equal to K minus pi plus 2. Okay, so that's the result. Let's give phase rule, and you will apply to the next page, and then you will see what happened. 好，这一页对，跟大家抱歉，就是我接下来就没有时间看，先看过一遍再来教各位，所以我可能就是当场去回忆一下这是什么东西这样。好，那总之 keep phrase rule 就是说，如果你有一个有一个系统，这个系统就是被你可以自己设计啊哈，你可以把它加东西进去，加 K 种材料，然后这 K 种材料它自己都有拍种 phase 拍种项 ，OK， 你都可以自己决定，因为这是你自己的材料嘛哈。但是我们加进去以后，它要是到达平衡的状态下的话，会有几种限制呢？我们来看一下，就是当下的状况是 T 或 P 是可以你温度跟压力是可以你自己决定的，所以这是你可以自己选择的，所以是自由度。对于人类来说，这是它自由度可以自己自行去变换的。但是等效的状况下，就是你选了 K 以后 ，K 个材料以后，那因为它的要等效嘛，每一个叫什么 chemical potential 都必须要相等，这样它才不会跑来跑去啊。刚刚不是说过吗 ？mu 都要是相等的嘛，哈，才会是 mu 啊 p 啊 t 都要是相等的，你才可以是不会动来动去的，它才是平衡的。所以说 mu i one mu i two 到 mu i pi 都要相等，那每一个之间都连了一个等号，表示说这前面是第一个式子，后面中间是第二个式子，然后到最后面又是第三个式子，最后面就是拍减一个式子，所以总共有拍减一个式子对于一个项来说，对项的转变来说，而且项转变而且是每一个项都有哦，而且每一个材料都有，你塞进去的材料都有，所以你要乘上 K， 所以这些是一定要符合的，因为你要等效，因为你要平衡嘛，对不对哈？所以这是你必须要去符合的。那另外一个就是这个材料的比例是你可以决定的啊，人类可以决定的，而且你也可以决定它是哪些项嘛，哦，所以它的组合是 K 跟拍 K 乘拍个，你都可以自行的决定哦。这要是这个材料要多大多少，这个的项要多大多少，都是你可以自己决定的。 但是它们加总起来要是等于1哦，等于1，而且你的这个项啊自己都要是加总起来都要是1，不然的话就变成110啊，这样不对吧所以说你有拍一个 equation， 你有拍一个项，它的项的比例都要是加起来等于1的。好，那这时候这都是限制嘛，蓝色是限制，黄色是你可以自由选择的，所以说你就可以把 F 就写成这样的式子，就会发现 F 等于 K 减派加2。好，那这时候就可以看到，就是说，如果今天你在做实验的时候，因为你有 degree of freedom 嘛，你要自己去改变你的选择的时候，你就可以自然而然的看出你有多少种可能。OK， so next we apply the Gibbs phase rule. F equal to K minus pi plus 2. Okay, so take carbon dioxide as an example. The phase diagram looks like this. So carbon dioxide only have one material, so K equal to 1. Okay, so F equal to 3 minus pi. All right, so let's take a look. So you see, for temperature and pressure, okay, the pressure and temperature is something you give. This is a degree of freedom, so that's the reason why you can plot as a diagram, as a variables. You can change. Right, as you can see, the triple point here, triple points here, you have 3 phases. So at that time, you have 3 phases coexist. So your phases is 3, pi equal to 3. So this is 3 minus 3 equal to 0. Okay, so you have no degree of freedom. So you only have 0D, 1 dimension, 2 dimension, 0 dimension is 1 point. Okay, so in this T and P phase diagrams, you only have 0D, 1 point for triple point for 3 phases coexist. But if you has 2 phases coexist, 2 phases coexist, which means that it is pi equal to 2. Okay, so 3 minus 2 equals 1. So it's 1D. It's a line. Okay, however, the other thing is that if you only have 1 phase, liquid phase, so pi equal to 1. So 3 minus 1 phase. Okay, 3 minus 1 equal to 2. So it's 2-dimensional, 2 degree of freedom. So it's 2D plan. Okay, so that's it. So that's how related to the human choose, and then how many possibility that we can draw in the phase diagram. 好，所以这一页就纯粹就只是把我的水嘞，在地板上，我们纯粹就是把phase rule apply 到这个 carbon dioxide 上面。那当然 carbon dioxide 就只有一个材料嘛，所以就是 K 等于1，那就等于是 F 等于3减派。接下来我们就来看，如果我们今天研究某种项是同时出现的，例如说三个都同时出现的时候，它的派等于3嘛，3减3就等于0，所以它就只有0，就是一个点，零维就只有一个点，那它就表示说它不会有在这个你的变数下，它是不会再有改变的，然后其他的地方也都不会有连续的 triple point 出现。那如果今天是两个项同时存在的时候，那它就会是3减2会等于1。那1表示一维，也就是 line 一条线。那如果今天是3减1一个 phase，那就是2
2的话 degree of freedom 就会是一个面。哦 Okay, so just well, it's a concept for you. The other thing is that next topic, mixing process for ideal gas. All right, so mixing ideal gas for pressure, for pressure. Because ideal gas, we assume that all the atoms, gas molecular, won't see each other. Okay, so you just put them into the container and they won't see each other. So their pressure is actually summed up together. Okay, so you can see if you have J, how many gas, J types of gas in the container. Okay, so each of them has its own pressure, Pj. Pj equal to mjRT over V. But for total P is total nRT over V. So you can imagine that sigma Pj, so that each of them, the pressure for each of the gas in the container, summed up together will be P. Okay, and you see P divided by N and J. So actually, very similar. The Pj equal to xjp. What is x? X is the molar fraction. Okay? So you can easily decompose the pressure, total pressure, into the pressure for each gas, each type of gas. Right, so this is for pressure. So now, I guess this is okay. This is not that difficult. Okay, so this is the first concept in this page. The first concept is for pressure. How about for the gas? For Gibbs function. Gibbs function. Okay. Gibbs function has similar composition. The G equal to NJGJ. So each of them has their own available free energy. And time them together, sum them up together. So it has a total value. So you can see specific Gibbs function of J constituent. You see the G is small letter. So you can imagine this is capital GJ divided by NJ. Very similar. Okay. So when they sum down together, of course, it will become total Gibbs free energy. Now, so you can see G equal to what? G actually equal to好累啊，加油啊 ！U plus PV minus TS, right? But here we are going to relate it to pressure. Pressure typically related to H, right? So when you see review 1, P15, and this is for ideal gas, right? Ideal gas. Your H minus H naught equal to T naught T CP dt, right? So you can substitute here, and then you will notice that here is U plus PV, right? Is H equal to CP integration plus H naught. So that's how we obtain this. Okay. Now
What's okay. So now we can use TDS equation. TDS equation 2 for ideal gas. Okay, and we can get TDS equal to Cp dt minus V dP, and we do the integration. We do integration, you can see S. I mean, we can divide T to the left-hand side, right? And we do the integration. So your S equal to Cp natural log T minus VdP. So T can use ideal gas to transfer into the pressure form. Okay, so you can get R natural log P. And of course, this is S naught is the integrating factor. Okay, so S, now we obtain that, we can substitute this to the S here. So we can say, oh, by the way, the H naught is the entropy, the enthalpy at 0K. So it's just a constant, okay? Now, after we put them into, substitute the S into the above equation, we find that, okay, CPT and H naught and Cp natural log T and S naught is actually a constant. It's actually a constant. Okay, so we can write down like phi T over RT equal to CPT plus H naught minus CPT natural log T minus TS naught. Okay, you see here, and there are all constant, So you can write down equal to RT natural log P plus phi. Okay, so now that's the small g equal to, small g has the RT times natural log P plus phi. The phi is a constant. Okay, phi is constant. And also the constant, when you define the temperature, you can obtain that. Okay, and then we will use this and this in the next few pages. Okay, so yeah, just give you some properties that we can use in the next page. 好，要讲这个，还是一句抱歉，就是我忘，就是我没有准备到这么远，我以为今天上课可以就很快结束了。那所以我刚刚看的就是会比较，我自己的反应会比较慢一点哈。好，那但是我敢保证这上面的东西都是正确的啊，只是我的逻辑或是讲话会比较不顺畅一点啊，这边请大家多多包涵。总之呢，我们等一下要去做，就是把两个 ideal gas 混合在一起。那要怎么做呢？就是首先要先去看它里面的几个特性。第一个特性是 pressure， 它会怎么变化？第二个就是 Gibbs function， 在这个混合的时候会有什么样的性质？好，我们来看一下。第一个，在压力的状况下呢，其实压力在 ideal gas 的就是合在一起的时候，每个 atom 是不会看到彼此，根本没差，他们根本看不到。假设看不到彼此的，所以说他们的压力就是各自加总就好了。那他们就是 Pj 等于 NJRT 乘上除以 V。好，这个我相信大家应该都没有问题。那你就会发现它的 NJ 就是它的比例嘛，对不对哈？它的摩尔
摩尔数，那 N 是它总 total 的摩尔数，是总 total 的压力，当然就会等于全部个别的小压力加在一起就是全部的压力吧，哈。那这样子一反算过来就可以知道，其实我们的每一个不同的材料的气体，它的压力就会是它的体积，不是体积，摩尔分率乘上它总压力，就是这样。这就是我们上面等到我们等一下要去 mix 真正的 ideal gas 的时候，它会有这样子的关系啊。这是第一个概念我们需要学习的。第二个概念就是我们的 give function。如果我们今天把 ideal gas 加在一起，会有什么样的事情发生呢？我们当然就会知道 G 就会等于 NJ GJ。我们就这之前写的嘛哈，在第8页就有看到了。那第8页我们写下来这里，那我们就会发现，这个 GJ 啊，其实就是大写的 GJ 除以 NJ 嘛，对不对？变成 specific 就是比的吉布斯能量哦。那所以乘上 NJ 当然就是各个气体的 G 大 G 加在一起，不就是全部的 G 嘛？好，所以这个式子其实就是还蛮 straightforward， 很正常。好，这时候我们要怎么样去写这个小 GJ 呢？这个 G 呢，其实它就会等于 U 加 PV 减 TS， 这个我相信大家没有问题。那这个 U 加 PV 又是 H 咯，这也没问题。这 H 呢，又在 ideal gas 下的话，它其实就是 CP 的积分嘛，所以呢，我们把它积出来以后，就发现，其实就是 CP 乘上 T 加上 H no， 就会是它的那个叫什么entropy at 0K， 其实就是它的常数嘛，最基底的那个常数。那减掉 TS， 这个没问题。好，这边写完了，但是 S 我们不知道啊，S 不知道怎么办呢？我们就靠我们的 TdS equation 的 for ideal gas， 那我们就写出，然后第二个 equation 它不是跟 CP 有关吗？那一定要用它嘛，我们写出它的 equation 以后因为这边是 ds， 这边是 s， 所以我们必须要做积分去得到它，得到 s 以后，它会长这个样子。好，得到长这样子以后，代入进去以后，我们就会发现，其实啊，我们的 S no CP natural log T 跟还有这两个 CPT 跟 H no 都是常数。这个常数我们就把它写成 phi T 除以 RT。大家会觉得，这 RT 怎么来的？是因为它啦，RT 乘上去以后就会消掉，才会有得到它们。我以前前几年啊，大概前5年的时候，我都忘记写这个 RT 了。反正我跟他说大家说这就是一个常数啊结果我写完这个式子，同学就发现，其实我少除一个 RT，我少除了一个 RT，没错了基本上就是这样。那这个 RT 是因为这边来的，它乘进去以后，正好就会等于这个蓝的荧光笔跟黄的荧光笔。OK， 所以我把这个黄的荧光笔跟蓝的荧光笔写成 phi 以后，你就会简化成 G 会等于 RT natural log P 加 phi。OK， 好，那这两个红框框里面的东西，等一下我们就会在 mixing procedure 里面用到。好，等一下就会知道，5分钟后。Alright, so 5 minutes left， 加油。So mixing process for ideal gas. We have initial state I and final state F. And of course, we have a wall between them. Before we take off the wall, you have N1, TP, N2, TP. No problem, just the same condition, right? The same temperature, the same pressure. We take out, we're just mixing them. And you see the GI equal to N1, G1I, N2, G2I. No problem, right? And we has this. So we G1I, G2I equal to this one and that one because P are the same, temperature are the same. The only thing is phi 1 is not the same, phi 2 are not the same. Okay, so this is initial condition. After we take off the temperature, take off the wall, the temperature is the same, P plus P2. Okay, no problem. N become N1 plus N2. So G final equal to N1 G1 F N2 G2 F. Again, we can use natural log RT natural log P plus phi equation. So this can also become here and there, but something different. P1 and P2 is P total P times the X1 here, right? And P X2. Okay, so now we can sum them up together, blah, 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 blah. All right. And compare with G equal to sigma mu J Nj. Now, actually, you can see mu equal to RT natural log P plus phi plus natural log X. Okay, so G equal to G plus RT natural log X. Okay. So in this case, we compare, okay? In this case, because we only have two constituent, two gas. In this case, GF equal to N1 mu1 plus N2 mu2 plus N2 mu2. So you see, compare with this. This is always true, right? We found that in previous few pages. Where is it? Here, right? So this one can be in this case because now your n only have two, right? So you have n1 mu1, n2 mu2, n equal to 2. So in this case, GF need to be n1 mu1, n2 mu2. But now your GF equal to these long things. So we can compare n1 mu1 such long things, n2 mu2 such long things. So mu equal to RT natural log P plus phi plus natural log X. All right, and if you decompose the phi, you will see RT natural log P plus phi, RT natural log P phi. Hey, it is G, right? So mu equal to G plus RT natural log X. So our chemical potential can be written as give-free specific gift function plus RT natural log X. OK？ 哦，好难哦哈，加油，最后1分钟就是我们把刚刚的 initial condition 一开始的状态 N1 TP N2 TP 中间有个墙，那这个系统的话，当然就是它的 G 就会是 N1 G1I N2 G2I， I 就是初始状态。我们把这个 G1I G2I 带着刚刚的公式没有问题。那如果是 final 的 S， 就是把墙拿掉了，拿掉完以后呢，它的 final 就是 N1 G1F N2 G2F， 一样我们可以带刚刚的公式，不一样的地方是它们的 P1 P2 是 P 乘上它的莫尔分率，这边也是 Px2 也是莫尔分率。写完以后，我们就发现 GF 会写成长长的这个式子。那我们 G 本身就有一个 summation 的这个公式是在可能第10页吧写的。我们这边有2个 m 等于2 1 n2 mu2。我们把这个东西跟上面这个长长的式比较一下，我们就会发现，原来我们的 mu 会等于这个长的式子。那这个长的式子前半部不就是 G 吗？后半部就是 RT natural log X。所以我们终于可以把 chemical potential 好好的表示了。chemical potential 等于是 G 加上 RT natural log X， 在我们的混合的状态下。好，哇，我们上到26页，也就是说这一堂课上了20页。 辛苦大家了，那我们下个礼拜见。OK，谢谢大家。快昏头了。哎。